about PPO, Proximal Policy Optimization. This method was introduced by OpenAI back in 2017, and honestly, since then, it's become sort of a default choice for a lot of reinforcement learning tasks. Now, why is that? Because PPO strikes a good balance. It's not too complicated to implement, it's more simple, efficient than older methods, and it is easier to tune, which means you don't have to spend endless hours trying to find the exact right hyperparameters just to get it to work. Now, the main thing PPO brings to the table is how it updates policies. Most of the earlier policy gradient methods had a problem. They made really large updates that could throw the training off course, and PPO avoids that by using a clipped objective function, which we will look at in a bit. But just now, for now, it helps keep the updates stable and not too aggressive. And let's quickly look at how it compares to what came before it. So we started with what's called a vanilla policy gradient, here also known as reinforce. The idea there is straightforward. You directly optimize the policy based on what actions it took and what rewards it got. And yes, it is simple and the math is not too bad. But the downside, it tends to have high variance in its gradients and it doesn't make very efficient use of data, so training is often unstable and slow. Then came TRPO, Trust Region Policy Optimization. This was a big improvement. Instead of letting the policy update freely, TRPO puts constraints on how much a policy can change in one step. That means learning is more stable and it makes better use of the data. But here's a catch. TRPO uses second order optimization, which means it needs to calculate or approximate the Hessian. That's heavy. And on top of that, it's tricky to use in combination with things like recurrent networks. Now PPO tries to take the best parts of TRPO but make it more practical. So what does it do differently? Well, PPO sticks with the first order optimization, just basic gradient descent, and avoids the heavy math from TRPO. It also reuses the same data across multiple training epochs, which improves sample efficiency. And the big thing is that it uses a clipping mechanism to prevent the policy from changing too much at once. So yes, you get more stable updates without needing that expensive math. And let's pause here and ask, what is the real innovation in PPO? Why does this clipping thing matter? Here is the formula that defines PPO's core idea. It's a surrogate loss that clips the probability ratio between the current policy and the old one. That ratio, it tells us how much a new policy is shifting compared to the one we just used to gather data. If that shift is too big, we clip it, and the clipping is based on a threshold, usually something like 0.1 or 0.2. So the update gets pushed back within a reasonable range, and this prevents large destructive jumps in policy space, which again helps with stability. The rest of the formula just multiplies by the advantage estimate, which is a measure of how good a particular action was in a given state. So we are still encouraging better actions, we are just doing it with a limiter attached. And so next, one thing that makes PPO more efficient than some older method is that it can reuse the same batch of experience data multiple times. And what is that? Instead of collecting fresh data for every gradient step like reinforced does, PPO lets us take a big batch and then run several epochs of updates on mini batches from that batch. So we don't waste samples. And that's a big deal in environments where getting data is expensive or slow. Now you might be thinking, wait, is not this what TRPO was doing with KL divergence constraints? Kind of yes, but PPO handles that differently. Instead of doing complex KL constraints with second order updates, it just clips objective. Optionally, you can still add a KL penalty if you want, and you can even stop early if the KL divergence gets too high. But the point is, these tricks help you stay close to the original policy, just like TRPO without computational overhead. And finally, PPO is usually with something called an actor critic setup. And what that means is you have got one network, the actor, which is your policy, and it tells you what actions to take. And then you have got the critic, which is basically a value function. It estimates how good a state is. You can train them together, sometimes even sharing parameters to make it more efficient. The critic helps the actor by providing advantage estimates, which are used in the last function we just looked at. And I hope that's okay. And let's look at our steps here. So we will look at how PPU actually works step by step, and this is the PPU clip version, which is the one most people use. We start by initializing two sets of parameters, one for the policy, that's theta, and one for the value function, which we call pi. And the policy is the part of that decides what actions to take, and the value function is there to help estimate how good certain states are. So now, in each training iteration, there are a few key things that happen. First, we collect a batch of trajectories by running the current version of our policy, not the updated one, the one we had before in the environment. So that gives us a batch of experiences, states, actions, reverse, and next states. Then we move on to the estimating the advantage values. This tells us how much better a certain action was compared to the average expectation at that state. And usually we use something called generalized advantage estimation for this part, GAE, and it gives us a smoother, lower variance estimate which helps with learning. After that, we take that batch of data and run several optimization steps on it. This is where the clipped surrogate objective comes into play. The idea is to find the value of data that maximizes this clipped version of the policy gradient, basically balancing between making improvements and not changing things too aggressively. So the formula you see there includes a mean operation that picks between the normal ratio and the clipped version, both multiplied by the advantage. And now, while that's happening, we also update the value function, and that's the critique using a simple regression. Okay, we try to reduce the mean squared error between what our value function predicts and the actual returns we saw. So we are pitting v pi to match the observed returns. And finally, once we have gone through these steps, we replace the old policy parameters with the new ones. So that's the basic PPU clip loop. Collect data, calculate advantage, optimize with clipping, fit the value function, and repeat. Now, in practice, most implementations don't just use that lost term. PPO is usually run with a combined objective that mixes in a few things. So let's walk through what that looks like. And first, there is same clipped surrogate objective. That's L clip, which handles the stability part. But on top of that, we add a value function loss L VF, which is usually just the mean squared error we just mentioned, and then there's another piece, an entropy term. That's S of the policy at states ST, and this term is added to encourage exploration, so the agent doesn't always go for most greedy option right away. We want it to keep trying out new actions early in training. And these three terms are combined into one total loss, and of course we don't want them to dominate each other, so we use coefficients. And I mean C1 and C2, to control how much each part contributes. These are just hyperparameters you can adjust based on how stable or exploratory you want the behavior to be. And I think that's okay. And here's some advantage parts. Okay, what are they? At first, PPO is pretty simple compared to the older methods. You don't need complex second order derivatives or constraint solvers. It works with plain gradient descent. And performance wise, PPO has been shown to match or even outperform more complicated methods on a bunch of benchmark tasks. And then there is sample efficiency. Since you are using the same batch of data for multiple gradient steps, you are not constantly needing to roll out fresh trajectories every single time. That helps a lot, especially in environments where collecting data is expensive. Stability is another strength. The clipping mechanism prevents those large, risky jumps in the policy. That's one of the reasons it's preferred over vanilla policy gradients. And also, PPO is flexible. It works well whether you have got discrete actions like in a board game or continuous ones like controlling a robot arm. And it parallelizes easily. You can run multiple environments at the same time, gather data faster, and train more efficiently. As for applications, it's been used successfully in a wide range of areas. You will find it in a game playing agents like Atari or more complex strategy games. It's also used in robotics, especially for tasks like movement and object manipulation. And in physics simulations like Mujoko environments, PPO is a solid go-to. And in recent years, it's been a big part of reinforced learning applied to large language models, particularly in fine-tuning time using human feedback. That's okay, and it is being used more practical domains too, stuff like managing data centers or optimizing networks. And some people are even experimenting with it in creative areas like procedural music generation. And okay, let's look at tips. There are a few things you'll need to deal in to get it working properly. And what are they? First, parameters, I mean hyperparameters. One of the most important ones is the clipping parameter, usually denoted as epsilon. Okay, you can see here. This controls how much change is allowed in the policy between updates, and a smaller value means more conservative updates, which usually means more stable learning. Something in the range of 0.1 and 0.3 is typical. Next, there is the learning rate. PPO is usually trained with adaptive optimizers like Adam, and a learning rate around 3e minus 4 is a common starting point. And that's it. Depending on your environment, you might need to adjust it a bit. Some tasks are more sensitive to this than others. Then we have got the number of epochs. That's how many times you go over each batch of data before moving on. PPO generally uses somewhere between 3 and 10 epochs, and it's a trade-off. More epochs mean you squeeze more out of each sample, but push it too far and you risk overfitting. And here, batch size. Bigger is usually better here, especially environments where the reward signal is noisy. Something like 10,000 or 100,000 time steps per batch is common in larger setups. Mini batch size is the size of each gradient step during those epochs. Again, there is a bit of flexibility, but most people go with something between 64 and 256 samples per step. For the discount factor, gamma 0.99 is kind of the standard. This means future rewards are still considered important, but not as important as immediate ones. And finally, we have got the lambda value for GAE, the generalized advantage estimator. A value of 0.95 is used most often. That gives a good balance between bias and variance in the advantage estimates. So those are your main knobs to turn, but just picking values is not enough. There are some practical tricks that help with performance too. And let's go over a few common enhancements, and normalization is a big one. By standardizing observations and advantage estimates, you help the network train more consistently. Without normalization, values can get out of range and cause unstable gradients. Another helpful tweak is value function clipping. This is kind of like clipping the policy. You limit how much the value function is allowed to change. That keeps it from chasing noisy targets too aggressively. And for initializing the network weights, orthogonal initialization is often a solid choice. It tends to give more reliable starting points, especially for deeper networks. And reward scaling is also something to keep in mind. If your rewards are too small or too large, the network can struggle. So scaling down to a reasonable range, say between -1 and 1, helps with training. Okay, that's that. And if your input features vary a lot in scale, you will want to normalize them too. That's what observation normalization is for. One last thing here is learning rate annealing. Basically, you start with a higher learning rate and gradually lower it as training progresses. And this helps the model settle into better solutions over time. And alright, so even with all these improvements, things can still go sideways, and that's where debugging comes in. When training PPO, one thing you want to monitor is the KL divergence, basically how much the new policy is changing compared to the old one. If it is jumping too far, you might need to back off on the learning rate or adjust your clipping value. And it is also good practice to track value loss, policy loss, and entropy separately. That way you can catch which part is misbehaving if training stalls or collapses. And make sure your advantages are normalized. It sounds minor, but if you skip that step, it can throw off the gradient updates. You will also want to check if the probability ratio is actually being clipped. Ideally, that should happen around 10% of the time. If clipping never happens, your updates might be too large. And I'm looking, entropy is another one to watch. It should go down over time, but not all at once. If entropy crashes too quickly, your policy is probably getting stuck in a narrow set of actions. That means it's overfitting and exploration is dying out too early. So, early in training, make sure the entropy bonus is doing its job. That's what helps the agent keep trying out new actions before it settles into a routine. And that's pretty much it for implementation tips. And that's all for PPO, and thank you for listening.